Top of the morning to you. All right, so I'm going to do an example using calorimetry. Now, calorimetry, I told you, is discovering the specific heat of something. Basically, it's mixing two things together. In this case, it's not going to be two liquids like it was with my coffee example. So, what we're going to start with, and the pre-setup, is going to be two containers. In one container is going to be boiling water, and in the other container is going to be a very small amount of 20 degrees Celsius water. That's room temperature water, approximately. Inside the boiling water, we're going to put a metal chunk, like let's say it's a gear. All right, you're a sprocket manufacturer for bicycles, and your competitor has come out with a new sprocket. They won't tell you what it's made out of. So one of the tests you can do is you can put it inside of boiling water and get it up to temperature. So put it in for about 5 minutes, and so the metal will become in thermal equilibrium with the boiling water, means the metal will be at 100 degrees Celsius. And then what you can do is you can take this hot 100 degrees Celsius metal and you can put it into a small container of water at 20 degrees Celsius. Now, to make this easy, let's have the sprocket weigh 100 grams, and let's have the amount of water that we put in the container be 100 grams. Furthermore, we probably want this container to be pretty well insulated, some sort of igloo cooler or something like that. So we put these two together, and as a result, they will come to thermal equilibrium at some third temperature. So now I need to draw this little sprocket inside the water, and there will be a different temperature. And from that temperature, in fact, let me specify the temperature. 34 degrees Celsius. From that temperature, we should be able to figure out what the specific heat is of the sprocket, and from that we can get an idea of what metal it might be, or what alloy it might be, because when you mix two metals, they have properties that are the average of the individual metals. So we need to do one of these calculations where the heat that goes into something equals the negative of the heat that goes out of something. Now, what is the heat going into? The heat is going into the water because the water is cool, the water warms up. Heat is coming out of the sprocket because the sprocket is warm and the sprocket cools down. So let's put the mass of the water, specific heat of the water, and the change in temperature of the water on this side. And on this side, negative mass of the metal, specific heat of the metal, and the change in temperature of the metal. W's and M's. I got to be careful that I don't make a W into an M or something like that. So let's get the numbers in really quick. 100 grams of water, and water has a specific heat of 4180. That's something I told you in the first lecture. It's a very important number. I need you to memorize it for this chapter. It's one of the highest specific heats there is. Now, the change in temperature of the water. Well, the final temperature is 34, and the initial temperature was 20. On the other side, we have 100 grams, and we have a specific heat that we don't know, so let's call it specific heat of the metal and leave it as a variable. And now the change in temperature. Now the final temperature of the metal is 34, and the initial temperature of the metal was 100. We got that 100 by submerging it in boiling water. And this is going to be a negative number, but that's going to cancel out this negative sign. So let's start working on this here. Alrighty, the 100s cancel. Let's do 34 minus 20, so this is going to be 4180, and 34 minus 20 is 14. The minus is going to cancel with the negative here, so we're going to have specific heat of the metal, and we're going to have 100 minus 34, so that's 66. Oh, we're getting close. This should be fairly easy. The specific heat of the metal will be 4180 times 14 and divided by 66. And I don't have my calculator handy, but I do have my cell phone handy. Okay, there we go. Cell phone calculator activate. 4180 times 14 divided by 66. 886.6, so we'll call it 887. And the units for that are joules per kilogram degree Celsius. Okay, that might help us figure out what metal it is. There aren't too many metals with that high a specific heat. If I look in my textbook here, I can see that there is a table of specific heats, and aluminum is 899. So maybe this sprocket is mostly aluminum. Nothing else is even close. Well, glass. I don't think it's going to be made out of glass, but that's about the only one that's that big. So this sprocket is probably made out of mostly aluminum. Hello, focus. Hello, focus. There it is. Mostly made of aluminum. Maybe there's something mixed in that drops the specific heat a little bit. That could be very useful for me. So that's how calorimetry is done. If we get a chance to do a lab, we'll do this lab, and I will give you a sink stopper from the old building, and you can try to figure out what metal it's made out of. Okay, there's one more thing I want to teach you about today, and it has to do with phase change. And then we'll do another example after that. Okay, when we talk about phase change, as you might have noticed from the Eureka videos, there are a couple different phases of matter. There's solid, liquid, and gas. Now there is one more phase of matter that I think you as a young person should know about, and that is if you take a gas and you continue to heat it, you're going to get a plasma. And in fact, I let the cat out of the bag. Solids have the lowest energy per molecule, and if you add heat to them and add heat energy, eventually they start jiggling so much that they break the bonds between the individual molecules and they become a liquid. Liquids flow, but they're still all one piece. And if you continue to heat a liquid, eventually it becomes a gas. And if you continue to heat a gas, it becomes a plasma. Now, what's the difference between a gas and a plasma? Oh, the plasma's hotter. Okay, let's start with duh. You've been adding heat to a gas, and you're going to get a plasma. Plasma means that the gas is now electrically active. In other words, you have given it so much energy that the electrons have started to leave their individual atoms and become a separate population. So the population of gas atoms, or ions, are positive, and then there's the cloud of electrons. And we use plasmas all the time. There's plasma inside the fluorescent light bulbs that are above us in the classroom. Okay, but there's something that goes on here that is interesting. So what I'm going to do is I'm going to make a very large graph, and we're going to fry up some ice. In other words, we're going to take a 1 kilogram chunk of ice, and we're going to pull it out of the freezer. And we're either going to put it in the microwave or we're going to put it in a frying pan. But I don't want to say frying pan because we want to heat all of the ice at the same time. If you put ice in a frying pan, the bottom layer will melt long before the top melts. In fact, you'll actually make steam out of some of the melted water before you even go. So this is going to be a heat axis. We're going to add heat along this axis. This could also be a time axis if we were adding heat at a steady rate. This is going to be a temperature axis, and it's going to be in degrees Celsius. This heat axis, of course, would be in joules. Now, we need a low that is the temperature of our freezer, and surprisingly, freezers are not at 0 degrees Celsius. If freezers were at 0 degrees Celsius, your food would constantly be melting and refreezing and melting and refreezing, and that is really not good for food. So they're substantially below. So let's say minus 10 degrees Celsius. That puts 0 degrees Celsius right here. And then the next thing we're going to need is 100 degrees Celsius and points above. So to begin with, and I'm gonna go ahead and make a little dotted line out here like this, and maybe kind of a dotted line over here somewhere to let you know where these levels are. Okay, so we pull the chunk of ice out of the freezer, and we stick it in our heating device, and we begin to heat it, and the very first thing that happens, and somebody in the classroom usually says, it melts. No, it doesn't melt. It's below the temperature at which it will melt. So what's going to happen first is it is going to rise up to 0 degrees Celsius. This will obey the equation Q equals mc delta T. The temperature is changing. The mass is the 1 kilogram, and C is the specific heat of ice. Now, the specific heat of ice is about 2,000. But Herbert, I thought you said the specific heat of water was 4186 or 4180. Yeah, that's the specific heat of water. This is the specific heat of ice. Ice has a slightly different specific heat, has a different structure. It vibrates in different ways than liquid water does. Once you get to 0 degrees Celsius, you continue to add heat, but the temperature doesn't change. It plateaus for a while. And that plateau is where the ice is melting and becoming water. Once you get all the ice melted and become water, you have to then raise the temperature of the water. So now your heat goes into raising the temperature of the water. And this obeys Q equals mc delta T. And the specific heat of water, 4180. Once you get to 100 degrees Celsius, the temperature stops increasing and it plateaus again. And all the heat energy you're putting in doesn't go into increasing the temperature, it goes into a phase transition, changing from a liquid to a gas. And then after you have changed all of the liquid water into a gas, then you can continue to heat it. And yes, a lot of people think that you cannot heat steam, which is what the liquid phase of, the gaseous phase of water is, but you can. If you trap it, you can continue to heat it. And in fact, superheated steam is used in power plants all the time. The specific heat of steam is also about 2000. One of these is 2010 and the other is 2020, as I recall. They're really not much different than 2000. So notice that there's a big difference in liquid water. Okay, let's talk about these plateaus. They have names. I said this one was where it was melting, but that's also known as what is it known as? It's known as when you go the other way, it's freezing. It's condensation. No, what is it called? Okay, this one is boiling, and that is also known as vaporization. What is the latent heat of fusion? Boiling is going this way, and fusion is actually this way when you have a liquid and it turns into a solid. That's called fusion. Now, these two plateaus cannot use the equation mc delta T because there is no delta T. So they have a different equation. They use the equation m, L, and L sub F for the latent heat of fusion, and this one uses Q equals M times LV, the latent heat of vaporization. The latent heat means hidden heat. That is the heat that goes into making the phase change that doesn't affect the temperature. The latent heat of vaporization for water is 2.26 times 10 to the 6 joules per kilogram. That's actually a very large number. Compare that to 4,180 joules per kilogram degrees Celsius, which if you do the full 100 degrees Celsius on this line here is not 4,000 but 41,000. This is 2 million. So this plateau should actually be much longer. If I did this to scale, I would need a giant sheet of paper. The latent heat of vaporization, however, fusion, I keep saying the wrong thing, is 3.34 times 10 to the 5 joules per kilogram. That's about 9 times less than that. So this plateau is 9 times shorter than this plateau. This plateau lasts a very long time. Okay, so I wanted to let you know that we use a different equation for the slopey sections than we do for the plateaued sections. I wanted to let you know that the plateaued sections exist, and that's where phase is changing. The temperature does not change on the plateau sections, hence the plateau, and that can be very useful. So putting ice and water together in one thing, like a drink, means you know the temperature is 0 degrees Celsius. In fact, I worked as an ice cream manufacturer for a while, and we had to calibrate our thermometers by putting them in a glass of ice water at the beginning of every shift, and they had to read 0 Celsius or 32 Fahrenheit. And that was a great way to do it. This is boiling water. Anytime you have a mixture of water and gas, boiling water, it stays at the same temperature. That's why cooking is often done with boiling water, because we know exactly what the temperature of boiling water is, and so we can just say, how many minutes do I put the pasta into the boiling water before it's done? They don't need to know the temperature of your boiling water. However, if you're in the mountains If you're in the mountains, the atmospheric pressure is lower, and this plateau shifts down a bit. And so, if you're boiling and you're making spaghetti after skiing for the day in Big Bear, then it's going to boil at a lower temperature. You're going to need to add a minute or so to the time in order to get your pasta to be done. Okay, let's be honest. You're probably making mac and cheese. I got it. So that is an interesting fact that happens. Um, what else can we say about this that hasn't been said about Afghanistan? So these plateaus exist at known temperatures. There are phase changes. You can spot them. Let's go ahead and use this. I'm going to use this number, and I want to show you how we can use. Oh my gosh, this piece of paper will certainly not work. We can use this to do something. So you'll recall that in our last discussion, I put some milk in my coffee to cool it down. That I had, example 2 on the day, I had some 80-degree coffee, and it was 100 grams of coffee, and I added to it a small amount of 25 grams of 5 degrees Celsius milk. And as a result, I got a cup of coffee, as I recall, was at 65 degrees Celsius. That's what we did yesterday. But I'm going to do something different. I'm going to take 100-gram coffee at 80 degrees Celsius, and I'm going to add to it a 25-gram ice cube. Now, this 25-gram ice cube, just for fun, I'll make it at 0 degrees Celsius. That's right at it's just about to melt. And we're going to get a cup of coffee when we're done. That's going to be at some other temperature, much lower. This we have to do in 2 parts. The first part we have to do is we have to say, let's melt the ice cube and see what that does to the coffee. So Q in equals minus Q out. The heat's going into the ice cube, and so let's put in the mass of the ice cube and the latent heat of fusion of the ice cube, because we're on that plateau. Here, we're starting right here, and we need to go across this plateau before we have water. We need to melt the ice cube. Okay, on the other side, heat is coming out of the coffee, so that's minus mass of the coffee, specific heat of coffee, and change in temperature of the coffee. So the mass of the ice was 25 grams. The latent heat of fusion is 3.34 times 10 to the 5. Oh, now can I get away with grams? I think I can. Minus mass of the coffee, 100 grams, and specific heat of 4180. And the change in temperature of the coffee is going to be the final temperature minus the starting temperature of 80. Okay, we've got everything we need here. Let's just get down to it. Okay, so 25 times 3.34 exponent 5 equals, and that's going to be 8.35 times 10 to the 6. And then on this side, we're going to have 100 times 4180 is 418,000. So that's 4.18 times 10 to the 3, 4, 5. That's times TF, and then that's a minus. And then we have to have 100 times 40 times 80. So multiply this by 80, and we get 33 million. So 3.34 times 10 to the 7. Okay. I'm sure you could do this in a more interesting way. I'm going to get this negative term over to this side, get this term over to that side. And so we're going to have 4.18 times 10 to the 5 TF equals, and then on this side, we're going to have 3.34 times 10 to the 7 minus 8.35 times 10 to the 6. Which turns out to be 2.51 times 10 to the 7. Now, dividing 2.51 times 10 to the 7 by the 4.18 times 10 to the 5 is going to give me my final temperature. Of 60. So we have melted the ice cube, and the coffee has gone down to 60 degrees Celsius. But wait, we're not done. You see, what we've got here is that we've got a chunk of water in the shape of an ice cube inside my coffee. The coffee's down to 60, but that water is still at 0 degrees Celsius. It's still at the other side of the plateau. So now we need to mix, and this is 60 degrees Celsius. Now we need to mix some 0 degrees Celsius water with some 60 degrees Celsius coffee. And that will give us our final answer. So then we'll have a homogeneous coffee at a certain temperature. So let's do that. Q in equals minus Q out. The heat is going to go into the 0 degrees Celsius water. So the mass of what used to be ice, specific heat of water, and change in temperature of the what used to be ice. And over here, mass of the coffee, specific heat of coffee, and the change in temperature of the coffee. All right, specific heat of water and specific heat of coffee are the same. So the mass of the what used to be ice is 25 grams. And the change in temperature is going to be T final minus 0. Over here, we have 100 grams of coffee. The specific heat canceled out, and we have T final minus 60. Remember, we got from 80 down to 60 already, so we're starting at 60 for this phase of the operation. Focus, focus, there it is. All right, so 25 TF is all that survives from this side, and on this side, we're going to have minus 100 TF plus 100 times 60 is 6,000. Bringing this to the other side, 125 TF equals 6,000, and TF is going to be 6,000 divided by 125. 6,000 divided by 125 is 48. Well, that's a substantial decrease, 48 degrees Celsius. And in fact, it's probably a little too cold for drinking coffee, but if you need to drink it in a hurry, you can put ice in your coffee. If you like the taste of cream, you can freeze some milk and put those milk cubes in your coffee, and that will not only cool it down so it can be consumed immediately, or also it will put that nice flavor in your coffee if that's what you're accustomed to. Okay, I went a little long with this one, but that's it for today.